Bismillahir Rahmanir Rahim. Welcome back, students. This is Hamza Noor, and in this video, I'm going to solve question number 3 of International A-Level Edexcel M1 January 2022 paper. All right, so the question says that a beam ADCB has length 5 meter. The beam lies on a horizontal step with the end A on the step and the end B projecting over the edge of the step. And then it says that the edge of the step is at the point D, where dB is equal to 1.3 meter, as you can see in figure 2. When a small boy of mass 30 kg stands on the beam at C, where CB is equal to 0.5 meter, the beam is on the point of tilting. So here the beam is on the point of tilting. So this means that beam would be in equilibrium, as you already know. And the boy is modeled as a particle and the beam is modeled as a uniform rod. Part A requirement is to find the mass of the beam. All right, so as you know, the fact that the beam is modeled as a uniform rod, which means that the center of the mass would be acting at the midpoint of this beam. Okay, so let's say this midpoint is over here. All right, so the mass of the beam is unknown. So the weight is mg Newton. And then at point D, we would be having a normal reaction force, which we are going to say RD. Okay. And you might be wondering that if there would be a normal reaction force at point A or not. So the answer is that there is no normal reaction force at A. Why? Because at this point D, you have the edge of the step, and this edge acts like a support. So how do we actually identify where to keep a normal reaction force and where not to keep a normal reaction force? Because if you place any object over here, if you place an object over here of a particular mass, let's say that object is such heavy that the beam is on the point of tilting. So when the beam is on the point of tilting, it would be tilting about the point D. So here we would have a normal reaction force. But if you place any objects along the beam at any point, so it is impossible that the rod will be tilting about the point A. It would be impossible in this case. So how to actually identify where to keep a normal reaction force and where to keep it not? First, you need to identify the supports. In this case, the edge at the point D is basically the support, because when you place an object over here, so the rod would tilt about point D. Rod has the ability to tilt about point D, so therefore we have a normal reaction force over here. But if you keep any object anywhere along this beam, so there is impossibility that this beam will tilt about point A. Therefore, there is no normal reaction over here at all. If this beam was something like this, I mean, let's say the horizontal step is something like this. You have a horizontal table and you have kept a beam over here like this. Let's say this point is A, this point is X, this point is D, and this point is B. So now the point D and point X are acting in the same way. They are the edge of the step. Okay, so if you place an object over here, so the rod has the ability to tilt about point D. And if you place an object over here, so the rod has the ability to tilt about point X. I mean to say is that if the horizontal step would be something like this, so here we would have a normal reaction at point X and normal reaction at point D as well. So these both edges would act as a support. Okay, so this is the correct way to identify where to keep the normal reaction force and where to keep it not. So as we can see that in this case, there is no normal reaction at point A. All right. And this support is just, I've made this as an imaginary object. Otherwise, it's just an edge and it is acting like a support. Okay. So here we have a normal reaction at point D. So what happens is that when a small boy of mass 30 kg stands on the beam at point C, a small boy stands at the beam at point C. He is having a mass of 30 kg. So the weight is acting 30 g Newton vertically downwards. So we are required to find the mass of the beam. So in this case, the most effective way would be to take the moment about point D so that this normal reaction at point D has no turning effect. Okay. So the moment about point D, so RD will be multiplied by 0. So it's most effective to take the moment about point D. Otherwise, you can take the moment about any other point, and then you would have, two equations connecting R and M, and then you can solve them. But that could be a little bit lengthier process. Okay, so the most effective way is to take the moment about point D. So if we take the moment about point D, so I am taking the anti-clockwise direction as positive. So sum of the moments acting anti-clockwise and clockwise, the sum of the moment will be equals to 0. So I've taken the anti-clockwise direction as positive. So if you consider this mg force, it is creating a rotating effect anti-clockwise. So mg multiplied by a distance from point D. So we need to find the distance from point D. So as we can see that this mg is acting at the midpoint of the rod. So this complete length is 2.5 meter. If we subtract 1.3 meter from 2.5, we will get this length. This is supposed to be 1.2 meter. Okay, so mg will be multiplied by 1.2. And then we have the RD force. But since we are taking the moment about point D, so there would be no rotational effect over here. So we will not consider this RD over here since we are taking the moment about point D. And then we have the 30G weight, and it is acting in the clockwise direction. So since I've taken the anti-clockwise direction as positive, so we will subtract 30G into what? We need to find this distance CD. So this will be 1.3 minus 0.5, which is 0.8 meter. This distance is 0.8 meter. So 0.8 will be multiplied by 30G. And this is subtracted from the earlier moment, and this whole thing will be equal to 0 since the rod is in equilibrium. So in this way, we are going to find the value of M. So M multiplied by 9.8 multiplied by 1.2 is equals to 30 multiplied by 9.8 multiplied by 0.8. So therefore, M will be equals to 30 multiplied by 9.8 multiplied by 0.8 upon 9.8 times 1.2. So therefore, M will be equals to 30 multiplied by 0.8 divided by 1.2. M is equals to 20 kg. So this is the answer of part A. And then we have the information that a block of mass m kg is now placed on the beam at point A. The block is modeled as a particle. Part B says that find the smallest value of x that will enable the boy to stand on the beam at B without the beam tilting. So here I'm going to erase the working of part A so that I can make some space for solving part B. mg is over here, and the value of m is 20 kg, as we have already seen in part A. And now what's happening is that a block of mass x kg is now placed on the beam at point A. So the block is placed over here. So the weight of this block is xg Newton. We need to find the smallest value of x that will enable the boy to stand on the beam at point B. So now the boy is over here, and the weight of the boy will be 30g Newton acting vertically downwards. And here we have the normal reaction at point D. What we need to do, we need to find the value of x that will enable the boy to stand on the beam without the beam tilting. So here, the most effective way again is to take the moment about point D. So I'm taking again the anti-clockwise direction as positive. And obviously the sum of the moments will be equal to 0. So I've taken anti-clockwise direction as positive. So first of all, we have xg Newton. So obviously we would need to find the distance AD. And since we know the fact that the distance between the midpoint of the rod and point D was 2.5 minus 1.3, meaning 1.2 meter. So it means that the distance between A and D will be 2.5 plus 1.2, which is 3.7 meter. Since I've taken anti-clockwise direction as positive, and xg Newton would create an anti-clockwise rotational effect. So therefore xg multiplied by 3.7. And here we have the mg force, and it will create an anti-clockwise turning effect. So this will be added. So plus mg times 1.2, and then we will subtract the turning effect created this by 30g force, because the 30g force will create a turning effect in clockwise direction. So we will subtract 30g times 1.3, and this whole thing will be equals to 0. And by this we would be able to find the value of x, and the value of m is 20 kg as we have found in part A. So x into g into 3.7 plus 20g into 1.2 minus 30g into 1.3, and this whole thing will be equal to 0. So if we take g as common, multiply by 3.7x plus 20 times 1.2, this is 24, minus 30 times 1.3, so minus 39, and this whole thing is equal to 0. So therefore g is gone over there. So therefore we can say that 3.7x plus 24 minus 39 is equal to 0. So therefore x will be equals to 39 minus 24 divided by 3.7. So 39 minus 24 divided by 3.7. Value of x is 4.054. X is equals to 4.054 kg. So correct to three significant figures, x will be equals to 4.05. All right, so here we have part C. Part C says that state how have you used the modeling assumption that the block is a particle in your calculations. So here we are just going to mention that the mass of the block is concentrated at a point. The mass of the block is concentrated at a point. Or we can also say that the weight acts through a single point. So we can make equivalent statements over here. So this was part C for 1 mark. So this was question number 3 of International A-Level Edexcel M1 January 2022 paper.